Welcome to This Explainer. Today, we're diving straight into a really profound paradox that captures exactly what goes wrong inside the human body during diabetes mellitus. It's a condition affecting literally millions of people, yet the core underlying mechanism, it's still surprisingly misunderstood. So we're going to break down the elegant but sometimes pretty flawed cellular machinery that governs how we use energy.
To get us started, I want you to picture this haunting metaphor from our source material. It describes a scene where a bird has tragically died in a cage. But, and here's the kicker, it didn't die in some barren wasteland. It died of thirst right beside a flowing stream of water, and of hunger right in the middle of a rich field. It's kind of like a rich man locked inside his own iron safe, perishing from starvation while completely surrounded by wealth. This perfectly captures the state of a single cell in a diabetic body. It's a starving entity, locked in a cage, entirely unable to reach the massive abundance of fuel resting right outside its door.
Because in a diabetic state, the body is essentially flooded with glucose. Your bloodstream is that rich field and that crystalline stream. The nutrients are absolutely there and in overwhelming abundance. But without the right key to actually open the cage, the cell remains stubbornly locked away from its vital fuel. The cell quite literally starves in the midst of plenty.
Now, to understand that missing key, we first have to look at the massive metabolic tug-of-war happening inside you every single day. Let's break down the major players here. On one side, we have insulin, which is the hormone responsible for storing fuel right after you eat. And on the flip side, we have the counter-regulatory hormones, glucagon, epinephrine, and cortisol. These guys are the mobilizers. They break down stored fuel during fasting, acute stress, or just long-term changing requirements, basically ensuring your body always has energy pumping through the bloodstream when it actually needs it.
What's really fascinating here is the stark, almost beautiful contrast between our main builder, insulin, and its primary rival, glucagon. Insulin is all about building and storing. It promotes glycogenesis, fat synthesis, protein synthesis. Basically, it's locking glucose safely into the vault. Glucagon, on the other hand, acts as the necessary counterbalance to break down and release that fuel when you're fasting. It sparks gluconeogenesis and glycogenolysis. They're the ultimate yin and yang of your blood sugar.
Moving right into Section 1, the structure of the key, unlocking insulin. Let's take a look at how the body actually manufactures this vital key from scratch. Because as you'll see, creating a master biological key requires a highly precise assembly line.
It all begins as a folded precursor called proinsulin, which is just a single, long, continuous chain. But to become fully active, it has to be significantly refined. It actually transforms into a highly functional two-chain structure of mature insulin. That's an A chain and a B chain linked together, leaving behind a leftover piece that we generally call the C-peptide.
The absolutely crucial takeaway here is that this is not some simple one-step process. First, the endoplasmic reticulum creates a raw material called preproinsulin. Then after a specific signal sequence is cleaved off, we get proinsulin. Next, highly specific enzymes, chief among them being one called convertase, swoop in like molecular scissors to cleave the dipeptide sites. That middle section, the C-peptide, gets completely removed and boom, the mature insulin molecule is finally forged and ready to unlock our cells.
And this brilliantly illustrates how modern medicine has learned to actually hack this system. By making just tiny, incredibly precise tweaks to that exact amino acid structure, scientists have created life-saving diabetes treatments. Take glargine, for example. If you just change a single glycine and add 2 arginine residues, you get a type of insulin that absorbs much slower, giving patients a steady, reliable baseline. But if you do the opposite and reverse just 2 amino acids, lysine and proline, you get Lispro. That one absorbs extremely rapidly after an injection, which is perfect for handling a sudden influx of food.
That brings us to Section 2, breaking the lock, the molecular mechanism. So we have the key, whether it's natural or medical, but how exactly does it force the cell membrane open to let glucose inside? Let's zoom right in on the cellular lock itself.
The real magic happens right at the insulin receptor, which comes with a built-in feature called tyrosine kinase activity. You can think of tyrosine kinase as a massive biological master switch located right on the inside of the cell membrane. When insulin binds to the outside of the receptor, this switch gets flipped. It autophosphorylates itself to trigger an absolutely spectacular chain reaction inside the cell.
The moment insulin docks, it physically changes the shape of the receptor. Those internal mechanisms, the tyrosine residues, trigger themselves. And this rapid activation instantly wakes up other internal proteins, most notably the insulin receptor substrates, or IRS. Basically, the key is securely in the lock and the tumblers are actively turning.
But the activated IRS doesn't stop there. It basically hands the biological baton over to another enzyme called PI3 kinase. PI3 kinase then passes the signal to protein kinase B, or PKB. This specific transmission pathway drives the signal deeper and deeper into the cell, priming it to finally throw its doors wide open.
This whole incredible multi-step cascade is ultimately building up to one big action. Hidden deep down inside the cell are these little vesicles. Think of them as tiny bubbles that contain glucose transporters known as GLUT4. The PKB signal commands these vesicles to rise all the way up to the surface and physically fuse with the plasma membrane. The lock is officially broken, the doors swing open, and glucose finally rushes into the cell.
Now keep in mind, this is a continuous, cyclical process. As long as insulin is hanging around, those GLUT4 transporters stay right there on the surface, ferrying glucose inside. But as our source material points out, the second insulin levels drop, the whole process runs in reverse. Those glucose transporters are literally swallowed back up into the cell through endocytosis, locked away in tiny vesicles once again. The cell cage is securely closed.
On to Section 3, Glucagon, the emergency override. So what happens when the situation is totally reversed? What if the body is truly starving, blood sugar is dropping dangerously low, and you desperately need to raise those levels just to survive? Enter glucagon. This is your body's ultimate emergency override. Secreted by the alpha cells of the pancreas, this single-chain polypeptide of exactly 29 amino acids is triggered by low glucose, stress, or intense exercise. And the coolest part, it works in rapid, powerful bursts. It's actually degraded by the liver and kidneys so fast that it has a short half-life of only 6 minutes. It gets in, does its job, and gets out. And instead of that tyrosine kinase lock we saw insulin using, glucagon relies on a totally different mechanism. When glucagon binds to its own specific receptor, it activates an enzyme called adenylate cyclase. This reaction immediately floods the inside of the cell with a messenger molecule known as cyclic AMP, or CAMP. This sudden surging wave of intercellular CAMP quickly activates protein kinase A. And once activated, protein kinase A initiates the rapid breakdown of stored glycogen, which is called glycogenolysis, and kicks off the synthesis of brand new glucose, known as gluconeogenesis. Essentially, the cell is entirely emptying its pantry, sending life-saving fuel right back out into the bloodstream to keep your brain and vital organs running. So ultimately, your metabolic health isn't just a matter of having one hormone or the other. It's all about the incredibly delicate ratio between these two powerhouses. A high insulin to glucagon ratio tells the cell, hey, times are good. It decreases CAMP, reduces active protein kinase A, and focuses on storing energy for tomorrow. But a low ratio? That sounds the alarm to burn everything just to survive today.
As we return to our opening metaphor of the starving bird and the gilded cage, surrounded by a rushing stream of resources, I want to leave you with a question to really ponder. Knowing the sheer complexity of this biological dance, from convertase forging the key all the way to the tyrosine kinase flipping the master switch, is the paradox of diabetes fundamentally an absolute deficiency of the insulin key? Or is it a relative inability of the cellular cage to actually turn the lock? The answer to that question defines not just the disease itself, but how we might actually, one day, cure it. Thanks for joining me on this explainer, and as always, keep questioning the science around you.